Before we dive into JR with JWE, let's take a step back and understand what JWE JSON Web Encryption is all about. First, it's important to note that JWE is not an OAuth 2 extension flow on its own. Instead, it integrates seamlessly with JR JWT secured authorization request flow to enhance security by adding confidentiality to authorization requests. In simple terms, a JWT JSON Web Token can be signed using JWS JSON Web Signature to ensure the integrity and authenticity of the data. In cases where asymmetric signing is used, JWS also offers a non-repudiation. This means that the party who signs the token cannot later deny their involvement, because only the private key held by the original signer could have generated the signature, which can be verified with the public key. However, when confidentiality is required, meaning we want to protect sensitive information within the token from unauthorized access, JWE JSON Web Encryption comes into play. When it comes to OAuth 2, the JR extension ensures the integrity and authenticity of the authorization request parameters through the use of assigned JWT, JWS, but in some cases, we also need to guarantee the confidentiality of the authorization request. This is where the combination of JR with JWE proves useful. In simple terms, JR with JWE works similarly to JAR, but with an added step. It encrypts the token. First, as usual, the resource owner initiates the flow. The client then performs the same steps as JAR, generates a PKCE and stores the code verifier securely, creates the authorization request parameters, including some sensitive information like an amount of 500 and the purpose rent payment that needs to remain confidential. Then packages these parameters into a JWT, encodes and signs the token to ensure integrity and authenticity. Here is the key distinction from JR. In JWE, the client also encrypts the token before sending it to the authorization server. We have covered the encryption mechanism in the asymmetric encryption lesson. For security reasons, we don't use the same key pair for encryption that was used for signing. Instead, we use a new key pair, one public key for the client to encrypt the token and one private key for authorization server to decrypt it. The client signs the token with its private key and encrypts it with the authorization server's public key. The authorization server verifies the signature with the client's public key and decrypts the token with its private key. Now let's see how this extension solves the security challenge from the JAR scenario. At the same point where the client redirects the resource owner to the authorization server, the attacker intercepts the token again and attempts to decode it and access the sensitive information. But it doesn't work. The token is encrypted and only the authorization server holds the private key to decrypt it, leaving the attacker very sad once again. Up until now, everything seems perfect, but we still face some challenges despite the security improvements. The first challenge comes after signing, encrypting, and packaging the token with the authorization parameters. Let's take a look at how long the URI has become. We have encountered this challenge before with the JAR extension as well. This approach can lead to issues such as increased URI length, which is problematic for mobile applications. And there is also the potential security risk if the URI is locked or intercepted. Even with signing or encryption, URI might be recorded in logs or caches, exposing sensitive information unintentionally. Moreover, let's discuss how difficult it is to manage the keys, renewing, revoking, and so on, especially as the architecture and the number of clients grow. Fortunately, there is another extension that addresses these challenges while continuing to secure the authorization parameters. We'll dive into that in the next lesson.